Bonjour à tous. Welcome to the second presentation of the day, which is a continuation of the first one that will be about autonomous driving. And it is for me a pleasure to present you the presenter, Patrick Perez, which is the scientific director of MobiliT.AI, which is an AI research lab focused on Valeo's automatic application, in particular self-driving car. Prior to joining Valeo, Patrick was a researcher at Technicolor, also at INRIA, and at the Microsoft Research Cambridge, and mainly his research focused on multimodal scene understanding and digital imaging. So Patrick, vous avez la parole.
Thank you, François, for the introduction. I hope everyone can hear me well. Not always ideal to give talks in these conditions, but better than nothing. Thanks for the invitation. And indeed, I'd like to talk about autonomous driving and discussing or mentioning very briefly some of the current challenges that we are facing, all the players in this industry. So for those who attended the talk of my colleague Xavier Perroton yesterday, you saw this nice video of the Valeo Drive for You experimental car handling the traffic of Paris before COVID, and using only mass-produced automotive grade sensors made by Valeo that you see on the top left, LiDAR, radar, cameras, and ultrasonics. But the car is not a commercial product, and there are in the trunk that you just saw. There are quite a few GPUs, for instance. So it's a platform with our sensors and experimental software. So let me move on, and so that's great. And if all these type of cars were already on our roads, that would be fantastic. First of all, it would mean that driving and transport at large would be safer, more efficient in time, more efficient in energy, and also more inclusive, extending mobility to some people who don't have access to mobility at the moment. So these are really the big promises of autonomous driving at large. However, there is a big caveat here, which is that autonomous driving is essentially a safety critical system which has to run in real time on embedded hardware and in an open world, so very unpredictable. And because of that, well, it's not quite yet a reality on our roads. And before it become something that we really use routinely in our societies, a number of things have to be, or conditions have to be met. First of all, so the systems and the AI which is behind the whole stack of the autonomous driving has to be essentially good. So what does it mean? So of course it has to be accurate, but not only, it should be robust to different changes in the environment. It should be able to generalize well or to adapt to new conditions, in particular when they are different from what has been seen at train time. So this is one thing. On top of that, the systems, because they go on road and that life of people is at stake, they must be validated, verified, and certified. So it's about regulation, etc. So it's one of the big topic of this forum, of course. And last but not least, in order for these systems to be accepted by not only the regulation body, but also the consumers and other stakeholders, it should be intelligible. And it's one of the drawbacks or the caveats with machine learning systems. They are usually considered as black box, although this can be discussed. And the last point, which is obvious as well, is that it has to be run mostly in the car. So I'm not going to talk about all these things. By the way, the last point might be discussed in the panel, which is scheduled later today. And I can just advertise as for the interpretability thing, a recent survey that we conducted and published on arXiv in my team on the explainability of AI system for autonomous driving. But for today, I will mostly discuss the first aspect, which is essentially the quality and the robustness of our perception systems. And in particular, one of the big and major challenges we are facing, and it was also mentioned in the previous talk today, which is training data. So as we all know, the current machine learning technology works especially well in when there is access to full supervision, meaning that you have training data, of course, which is large enough and with a good coverage, which is already hard to acquire in some case, hard in terms of time and cost, and also of safety. And on top of that, you are supposed to annotate everything if you do fully supervised learning. And this is very, very time consuming, very costly. And sometimes for some tasks, it's not even possible to do that by hand. Take the example of depth estimation. You cannot specify by hand what is the depth. So you need other sensors. So it's a complex process. And just considering one key or archetypical perception task that we face for autonomous driving, which is semantic segmentation of the images that are collected by the front-facing or all the other cameras on the car. And so the task is really to predict the semantic class of each pixel. And to train the systems, you need this type of annotation, which is very difficult to get. It takes roughly, I mean, in terms of time, it could be half an hour to annotate by hand such an image, such a scene. So these are examples from the cityscapes. And in this example, for instance, in cityscapes, there are 5,000 fully annotated images of this type. And on top of that, you have 20,000 more images, which are more roughly annotated. So very difficult to get. And on top of that, it won't ever be sufficient because of the mere nature of autonomous driving in an open world. So there is a race which is doomed to be lost. So how can we go about this challenge? One answer or part of the answer has to be found in the machine learning literature. So there are many other ways to supervise the training of a machine learning model. There is a long list here. I'm not going to go through it in detail. I'm just going to highlight a few things. For instance, you can very well learn models by having only part of the data which is annotated, so it's semi-supervised learning, or only some aspects of your examples which is annotated, it's weakly supervised learning. So there are many ways to do that, and it's very powerful. Another very interesting line of work and extremely popular at the moment is self-supervised learning and unsupervised learning. And the question is how to learn interesting representation by just using raw data that you can also access on a large scale. So obviously very, very interesting. Alternatively, you might want to learn things from just a few annotated examples. It's called few shot learning, or no examples at all if you have some knowledge to compensate for the lack of data, and it's called zero shot learning. And these things are, I might show some examples of that as well. And another extremely broad and powerful class of methods is transfer learning, where you transfer from another domain, another task, another data set, etc. It's also about how to reuse or to use efficiently all the data you can put your hands on. And in particular, in order to do transfer learning, transfer learning in particular is useful for the following tasks. You can use that for zero shot learning, few shot learning, etc. So it's really a cornerstone for many other types of supervision. And conversely, in order to do transfer learning, you can benefit from other tools. Typically, self-training that I'm going to mention a bit later, which is about using pseudo-labeling, is very interesting for transfer learning. Distillation is a very well-known way to do transfer learning. And self-supervised and unsupervised learning, when used, for instance, for pre-training, is a way to already transfer some knowledge to the downstream task that you want to finally address. And then on top of that, you can combine different types of supervision. For instance, when you do active learning, it's in the context where you have a large data set to be annotated and you do that iteratively. Well, at each point in time, you have part of the data which is annotated and the other one which is not. So it's an actual semi-supervised learning setup that you can leverage. Self-training that I already mentioned turns out to be a key tool for semi-supervised learning, domain adaptation, and active learning, and I will give one example of that. Right, so now diving into one or two examples of things we do in the team, I'm taking here the problem of semantic segmentation with domain adaptation. So the problem is the following. There are many situations where the data you have for training follow a certain distribution in terms of conditions of driving, weather, etc. And it's different, or it might be different at runtime. So it's called the domain gap or the domain shift. And the assumption is that you have a source domain and a target domain which differ just because it's different weather or it's different time of day and lighting, or it can be different geographic location, or it can be because you have different sensors. In this case, it's a bit of extreme. I go from a pinhole camera to fisheye camera, but this is a real use case. And another one which is extremely important is when you train on synthetic data, and you of course want to use your system in the real world. So all these examples are instances of what we call domain gaps that we have to face for getting robust systems. And in particular, if we just look at the case of synthetic to real domain gap, so imagine that your system is able to produce the following semantic segmentation on a new synthetic test image, and it looks good. And if the same system is run without any adaptation on real images, this is what you get, which is pretty disappointing and not very comforting in terms of safety of the overall autonomous driving system. So we have to do something about it, and there is a lot of literature on domain adaptation, and in particular what is called unsupervised domain adaptation. So in UDA, the assumption is that at train time, you do have examples from the source domain which are annotated. This is what you see on the left. In this case, is synthetic data. So very easy to get the annotation automatically. And on the right, it is something also you have at train time, which are examples from the target domain, but devoid of any annotation. So hence the terminology. So one piece of work that we did at CVPR in 19, but again, it's part of a big research thread in the community, is the following. So again, we have our favorite semantic segmentation neural network, which is trained first on only synthetic data for semantic segmentation. And when tested on a new synthetic image, it gives this type of satisfactory segmentation, and on a real one, not so satisfactory. And the point here is how to reduce the gap, and or at least to reduce to improve the performance in the on the target domain images. And one other thing that we did is to look at the uncertainty of the prediction. So at each pixel, you can compute, for instance, the entropy, which is one indicator of the confidence that the network has in its own decision at the pixel level, and it's pretty good for the synthetic image. So the uncertainty is really focusing on a remote location and on boundaries between regions. And it's a lot messier on the real image, not surprisingly. And the idea that we had is to try at training time to favor or to favor lower entropy in the decision on real images, and hence to get better results as on this example. And in order to do that, I'm not going to into the details here, but just to show the typical type of unsupervised domain adaptation framework, where on the same at training time you have both at the top unlabeled target examples, and you have at the bottom labeled source domain examples, for which you can have the classic segmentation loss, but for the other ones, you don't have the ground truth, so you have to do something. And what we do here is to have different losses in order to enforce low entropy at the pixel level. And at the same time, we have another one, which is adversarial, and adversarial training is very powerful for domain adaptation, where we essentially we have a discriminator which has to decide whether essentially the entropy map, which is output by the network, is associated to a source or a target input image. And it does work pretty well. And you see here qualitative results, and they do translate into good numbers, which were state of the art at the time of publication, but the competition goes very fast. And if I can play the video, it's probably easier to see. So you really see the improvement, and also you see the reduced entropy map in the image map that is on the left top left corner. And then we had extension of that, where we also show that, at least in the case of the where the source domain is synthetic, you have actually other information which can come for free about the scene. In this case, it's what we used is the depth in the scene that we have in the synthetic data, and so we at train time, we train for an additional task, so it multitask learning in effect, but this task is only in order to force the backbone of the network to learn better features for the main task, which remains a semantic segmentation. And using this type of additional information at train time is called also learning with privileged information, which dates back to work of Vapnik and colleagues more than 10 years ago. And it does improve the results, and it's not at least spectacular here, but if you look at the yellow box, the details around the cyclist, you see that the segmentation is better by using this improved approach. And these are qualitative results. I'm going to skip that, and you can find in the papers at the end of the slides. I have all the references, and also you can find the comparisons to the competition. Another interesting way to attack supervised domain adaptation is to leverage the fact that most of the time for autonomous driving, we have multiple types of sensors, and typically cameras and LiDARs, which have different pros and cons. And in particular, for nighttime perception, the LiDAR is less impacted by the low light, of course, obviously, as compared to the camera. So one extension that we had of our research on domain adaptation is to leverage that for the following task, which is as well a key task in perception for autonomous vehicles, which is 3D semantic segmentation of 3D point clouds. And in this case, we can address the same task either by looking just at an input image, so it's a 2D to 3D type of task, or we can really take as input the LiDAR 3D point cloud and try directly to segment it. And we use these two streams, these two modalities, in order to get a better domain adaptation, in particular from day to night. And this is and one of the ingredients that I want to mention. So interestingly enough, so we have two streams doing the same task, and each one can teach to the other one interesting things. So we have a cross-modal type of learning. And another aspect that we use is called this is what you see here with the loss, which is called LPL. PL stands for pseudo labeling. Is we use self-training in the process in order to retrain the model. I'm just going to skip the examples, but I just wanted to highlight this pseudo labeling mechanism here, which is very useful at large, and we leverage it here for explicitly for domain adaptation. So pseudo labeling is a self-training techniques by whereby you have already a model which has been trained, and then you can use it to sort of automatically annotate part of the rest of the data which is not annotated, and this creates what is called pseudo labels, and then you can refine or retrain completely your model based on these new annotated data. So it's something which is well known in semi-supervised learning, where it's quite natural because you have by construction only one part of the training set which is annotated, and actually it can be used as well as we show here for domain adaptation. But in that case, what is not annotated is the target domain data. And another one difficulty, of course, it's a bit of a risky business, because if the automatic annotation is not good, then your model can learn garbage. So in order to stay on the safe side, you need to make sure that you only retain pseudo labels for which you are fairly confident. And this is one of the challenges that we looked at, which is how to identify this confidence in the pseudo labels.
10 minutes left, Patrick.
Yeah. So one classic way is just to look at the what is the score of your prediction, the max score of your prediction at pixel. But it's not a very good proxy for confidence. Another one which we explored, which is again based on entropy. So looking at the dispersion of the prediction, of the class prediction at the pixel level, and if not very, it's not very visible here, but if you look at the pixels which are retained by the method, the second method, it retains more confident pixels or better pseudo labels. You can examine that when you have the slides that I will share. And this different, and a last method that we explored, which is more more ambitious and goes way beyond this problem. It's really about how to estimate or predict the confidence in the prediction. Let me maybe skip to this slide. So, which we presented in 19, sorry, at NeurIPS, is a system where, given a network for a given task, we want to train an auxiliary network which is going to predict what is the confidence. And effectively, instead of looking at what is the max class probability, at train time, we know what is the ground truth class, so we can look at what is the probability or the score for the true class, and we essentially learn an auxiliary network which has as a task to predict this value. And you can even, so this network use the encoder of the main network, or can also be fine-tuned, and this is a very effective way to predict the confidence. Let's see, for sake of time, I'm going to just to move to this slide, and then I will stop with just the list of publication and the photo family of the team. So this work is about data augmentation using GAN. So the problem is how to get more examples of real scenes with pedestrians in particular, with different poses and or in rare conditions, in order to learn better detector. And so what you see here is the result of this work with Prague University, where in each scene you have at least one pedestrian with fake. It's a synthetic one, which has been generated by a generative adversarial network. And we control the pose and the appearance, so we can create this way and augment a real scene to create a new more data. And let me show you on this example. So we train a pedestrian detector in a low data regime, and what you see in blue is the test time detection by just the vanilla detector, and in green all the false negatives that we recover after training on these augmented data with fake pedestrians. So it's quite effective. So let me finish with this nice family photo of the team. We are 25 people, mostly in Paris, and 1/3 are PhD students, and we have great collaborations with many academics. And I can just stay on this slide for to take the question. And this is the list of the papers that I just mentioned on my presentation. Thank you very much.
Okay, thank you, Patrick. Very nice presentation. I really enjoy it. So let's go to the question. So the first question is from Ralph Nahaus. Sorry if I didn't say it correctly. So it's maybe a more practical question related to what you describe in a high level. So how the machine will adjust to unexpected environment like snow in the deserts or something like that.
So the answer is probably if adapt means that realizes that there is snow and knows what to do, probably no.
But
I
I mean,
guess
in a desert, so it's some kind of unexpected
Exactly.
situation.
So my point is that as in AI in general, the capacity of our machine learning systems to react to the extremely rare and predictable situations is quite limited. Generalization is already limited even if you are in the same domain sometimes, unfortunately. So there is a lot of progress to do before we can reason about these unexpected or extremely unexpected situations. Part of the answer might be might be on relying not only on pure data-driven machine learning, but also having some mitigating that or combining that with knowledge base or reasoning capacity. And it's clearly one of the current challenges of AI at the moment, how to combine things. But another part of the answer is, and it's also related to, it was very fast, but when I briefly showed one way to learn a sort of an auxiliary model to monitor your main task to decide whether the decision is should be considered as confident or not. I think it's already important to at least be able for such system to decide that they don't know. And this is already a challenge. So, and in that case, having some good or accurate estimate of the confidence of the main system is allows many things. It allows maybe to hand over or to give the control back to a human driver, if any, or to teleoperator if there is, or to other sensors which are not, say in this case, not perturbed at all by
Yeah,
the presence of the snow, or these kind of things.
but even if in the situation that you allow the system to say, well, I don't know, so take the command.
Yep.
How can we detect that we are completely out of distribution?
Well, that's, yeah, I guess it's a long-standing question even in statistics. So there are ways to or tools to decide. So either you want to decide by looking at the behavior of your system, because you know that the typical output that you should get, or the typical intermediate representation that the system is supposed to produce based on data, if they are from the training domain that you know of, or you can have external or additional modules which are just in charge of monitoring the distribution and to decide based on statistical criteria, even hypothesis testing, whether you are or not on the right distribution. And of course, this case is a clear one in a sense. What is even more annoying is that this being aware of it can be even ill-posed, whether it's you are in the distribution. I mean, having one scene element which is very rare does it mean that you are completely out of distribution? If you have an unexpected object or animal in a scene which otherwise is completely normal, yeah, very difficult.
And also we are far from being able to have a real certification process of that AI, right?
Related to the same question. So
again,
yeah,
it's the deal project that we are talking about.
of course. So it's these are really complete research projects on the agenda of many people, labs, and organizations. And it's true that as soon as you look into this type of really safety critical systems, it becomes even more um, yeah, sensitive. But another answer is really, but it's not the end of the story. But being able to do a lot of things with synthetic or partially synthetic data does help, but getting formal guarantees about the behavior of, say, a neural network which does one perception task, which is a submodule of a full system, is really a daunting task.
Yeah, we have many other questions in the chat, but I'm afraid that you are short for time. So I thank you again, Patrick. Can you maybe just give answer directly on the chat for the two nice questions that are still left?
I'll do that right away.
And thank you for the presentation. And I think we have to chat also together offline.
With pleasure.
We will share ideas. Okay.
Thank you everyone for the attention. Bye-bye, everyone.
Thank you. Bye-bye.